Yeah, don't worry.
Hi,
I'm in
Tobias.
a very disorganized. Hello, hello. I'm in a very disorganized room right now, so please just bear with the background. Yeah. So yeah, my name is Tobias, whoever is pronouncing it in any way. Yeah, you can pronounce it in any way, but short form is Toby. Yeah, again, Tobias Thomas, and
Okay.
as Bami has introduced, I am retiring, but I'm a research assistant at the IBM Institute of Advanced Studies. And in my work there, I usually, I'm working inside the Python side. So I'm doing some stuff inside Python. And also I'm an embedded systems engineer where I work at a local factory and local company called Pumzi Devices. And they make smart medical hardware, like things that smart devices for hospitals. Other than that,
Something
I'm
like
also
AI,
an
yeah.
open, yeah, they make smart stuff. I don't know if
Yeah,
my
yeah.
network is fine. Is my network okay?
Yeah, your network is fine. It's just that your face is like blurry.
Oh yeah.
I don't know why
So
that is
also,
happening. Maybe it's my network.
no, I think I'm using the laptop's microphone because I don't have studio quality setup here, you know. So
It doesn't really matter.
everything is just minimum at this time. Minimum microphone and minimum camera. Everything is just, I think you can even see the reflection of the screen in my glasses. So everything is just minimum. So that is it for me. And so today I was invited by the Tunga people. I call them Tunga people. So to talk about asynchronous programming in Python. I wanted to show some slides, but I don't know if it's going to be possible.
Yeah, you can. Yes, you should be able to share your slide. Someone is raising hand. Okay, so Tobias, just 1 minute. Somebody is raising his hand. Victor Godwin. Hi, Victor.
Hey.
Hi.
Hi, can you hear me?
Do you have a question? Yes,
no,
we
no.
can hear you.
No, I just joined it, so I just wanted to be sure here. That's all.
Okay.
I don't know if I was late.
All right, thank you. Yeah, you're a bit late, but it's fine. So while Tobias is like going through the slides, you all can like introduce yourself and what you do in the comment section. Thank you very much. Right, yeah, so we'll get to know each other. So Tobias, the floor is yours.
Yeah, I'm trying to share my screen, but I can't. It's saying host disabled participants share screen.
Oh, yes. Oh wow.
Yeah.
Oh wow. Okay. That's the thing with Zoom. I don't think I can really know how to. All right. So you should be able to share a screen now.
Okay.
Can you do that?
Yeah, I can now.
All right. Thank you very much.
This is happening. Oh, sorry. I'm trying to like set it up really well. I was just working on the slides and a little bit disorganized. But I want this to be more of a question and answer kind of thing. So my slides are really few and they just talk about the basic things. So like I want to get done with the whole entire concept in just a few minutes, and then I'll open the floor to everyone to just ask whatever they feel like asking.
All right, fine. Thank you very much.
So the slideshow is trying to open. And wait, it's open with no, I'm not open. Just taking over my screen now. Okay. If this doesn't work, because also it's my first time being in a Zoom thing, but if it doesn't work, I'm just going to tell the whole story without showing slides because they're not even perfect.
Oh, but can you share it now? Is it working?
Yeah, yeah.
Okay, you're sharing your screen now.
Are you seeing anything on my screen?
I'm just seeing Tobias has started sharing screen, but okay, yes, now we can see your screen.
Okay. How big or how small is it? I don't know.
Nah, I think it's okay.
I'm just moving around that. Okay, so yeah, my name is Tobias Thomas, as I introduced, and I'm talking about the synchronous programming in Python. And next slide. That is, can you even be able to see anything? All right, we shall just go with that. So
Yes, we can see.
what is asynchronous programming? Yeah, so asynchronous programming is a development of programs. I don't know if this is the first time that people have heard about this. I think it's something that maybe has been around for a while, but no one knows it really well. So asynchronous programming is a way of building programs that run tasks concurrently. Now, in this case, concurrently is a program that is able to run different activities, like many activities at a time, but one at a time, not all of them at once. So that is the difference between concurrency and parallelism, because it's a very, very confusing statement. It's a very confusing paradigm for some people. When you talk about multiprocessing, people like, are you running tasks at the same time? No, this is concurrency, where we run many tasks in the same period of time, but one at a time. And it has been implemented in very many languages. For example, in C++, in JavaScript, Lua, and Python, C#. Many languages, modern languages now have the ability to write asynchronous code or asynchronous programs. So one of the central concepts of asynchronous programming is that it's non-blocking. I would want to dive into the meaning of non-blocking sometime in the future. But by non-blocking, I mean that the code that is running is not supposed to, I don't know if I'm being clear, my internet is breaking up. It's showing me there, my internet is breaking up. The code that is running is supposed to block or stop another code from. That is basically what non-blocking means. It means that every task that is being run is supposed to be run independently and should make way for another task to be run in case it needs to be run. That is the concept of non-blocking. And asynchronous programming is the central theory behind what we call event-driven programming nowadays, where you have a lot of events and there are systems that respond to those events. And event-driven programming is being used in GUI applications, in big servers, in research. It's used everywhere. So one thing is that asynchronous programming does not increase your CPU capacity, but it helps you utilize it to its full potential. And I think maybe we shall talk about this more as time goes on. So, slide. Why is asynchronous programming important? So in this case, I'm going to tell a story. And this story is starting from the birth of the internet by Tim Berners-Lee, who was working at Sun Labs by then. And it was back then in 1989 when he had thought about, why don't we try to share ideas between research labs and academic institutes, because it's been hard to share information all around the world. So his idea brings the birth of the internet. And from 1989 to 1994, he wrote a web browser, he wrote a web server, he wrote the first HTTP protocol and the HTML and everything that is supposed to run a fully functional internet. And he goes out and his work is appreciated by Sun Lab, and some other, SunLab is in Switzerland, but it's appreciated by people in the US, in the UK, and what. So the internet. And one of the characteristics of the servers back in the is it was accessed now become a little bit of a success, and now governments are starting to use it, and now research academic institutions are starting to use it. Private enterprises like banks are starting to use it. So now there's a lot of traffic going into the internet, and now the servers that were the server that Tim Berners-Lee had written wasn't enough to handle the load at that time. So the next server is written, which is the Apache server that we know up to today. And the architecture that it uses internally is that for every connection, it spawns a thread of execution on the OS. And each thread of execution has a performance cost that it incurs on the operating system. But still, at that time, the internet was still being accessed by very few people. So the threads were enough, we can say. You can spawn 500 threads, because back in the day, maybe 500 people could access the services at once. And the operating system could be able to handle it. But now we come into the new age where internet is now everywhere. From 2002 to 2022, where we are right now. The internet has now become ubiquitous. Everyone is using it. We're even using the internet right now. So the communication is by everyone. And the servers back in the day that were using multi-threading could no longer handle that kind of load. So new research had to be done in how we can build servers to scale. I think you've heard of the word scalability every now and then, scalability here and there, scalability, what and what. So yeah, the servers have to scale to the load of the people who are accessing the internet. And that is when asynchronous programming began taking shape. We see the famous battle between the Apache web server and Nginx web server. The Nginx web server employs the asynchronous kind of programming, where it uses, okay, I'll try to explain all that maybe in the next slide. Today is just an overview, but it uses asynchronous techniques to be able to handle millions of requests at the same time, which would be better, far better than how Apache Server was handling it before. So, oh. The next slide is not happening. Oh, yeah. So then here we are. So how do we write asynchronous code? That is one of the questions. So asynchronous code involves two main parties. One is a coroutine, and the other is an invert loop. So a coroutine, I'll try to break it up so that you can understand what it is. We have three kinds of functions. Okay, we have functions in programming. They can be called routines, especially if that function is being called over and over and over again through the application's life cycle. So if a function is being called frequently, that function has now become a routine. Now, under routines, we can have subroutines. So those are internal functions that are being called inside another bigger routine function. So that is a subroutine. But under routines themselves, you have coroutines. Now, coroutines are functions that have the ability to be paused and re-executed at will, so that they can be executed anytime in concurrence to each other. So that is, I don't know, if you haven't understood, we shall go through the question and answer sessions that you can ask. And then we have the event loop. Now the event loop is the one that gets all the coroutines all functions and runs them separately until they are completed. I don't have anything to add, but that is the nature of an event loop. It gets all the coroutines, millions of coroutines, and runs them concurrently, one at a time, until all of them are completed. So a coroutine can represent a connection, can represent a server connection, can represent a client connection, can represent any task that is being run by maybe the program at that time. Could be a server, it could be a game, could be a GUI, could be anything. So in Python specifically, things are now widespread inside. Like I told you last time, we have event asynchronous programming has been implemented in many languages, Rust, what. So that means they have also a concept of coroutines, and they have a way they build their coroutines in the language specifically. But here we're talking about Python. So implementing coroutines in Python, you would need async and await. And on the function declaration, and that will tell Python to compile it as a coroutine. And then we have so Python will compile it as a coroutine, and as a coroutine, it to pause and execute it later on. Like as it is running your database, and you want to search through. So you can search maybe the first 5 and pause, and then another one can search maybe somewhere else, and then it pauses. Then another coroutine can come in and do some, then it pauses. Then you come to previous search place, and it continues from where it stopped. Like it had stopped at 4, it begins now going to 6, 7, 8, 9, 10. Then maybe it can stop there. Then tell another coroutine now you can run. Call it cooperative.
Oh. Okay. Sorry guys. It's in. Okay. This is back. Something has network-ish. Tobias, are you back with us?
I'm back.
You are still breaking though.
I don't know. Yeah. Is my screen visible?
Yes. No. I can't see your screen, but I can see you, and you are breaking.
My internet. I don't know how to fix it. I don't know how to fix this internet problem. But is my screen visible now? Because I can see it here. It shows it's sharing.
No,
Really?
It's not visible yet, except if I'm the one not seeing it. Can any other person see this? Can any other person see his screen?
And also, it shows that I'm sharing it.
Yeah, it's showing that you are sharing here. So just wait a little bit. I'm so sorry about that.
I think it's my problem this side. I don't know, I'm not sure. But I think let me just continue because I wasn't even, I'm just talking. So like if you're hearing me, let me just continue. So yeah, the coroutines are run in a single thread of execution. So that means in comparison to how Apache Server was doing it back in the day, For every person who connects to an Apache server, it spawns a thread, an OS thread. And that OS thread is very expensive to maintain by the operating system. So if there are 60,000 people who have connected to the Apache server, it will spawn 60,000 threads to run on the operating system, which will impose a lot of strain on it. So what synchronous programming does is that it takes off that load from the operating system and brings it into a coroutine. So if there are 60,000 connections, there shall be 60,000 coroutines that are managing that connection. But they shall be running in one single thread of execution of the operating system. So that means that there is no strain on the operating system thread. And you can even use 4 threads only. You call them worker threads, like Nginx does. Nginx has 1 main thread and 4 worker threads. And those threads are enough to handle millions of requests, up to 6 million requests, only 4 worker threads, of which the Apache web server would need to spawn 6 million threads, which is almost impossible for the operating system to handle. So that is the reason that's why some of these coroutines are advantageous. And it implements cooperative multitasking, like I told you before, where one coroutine shall be running in concurrency with another. It will run at some points, pauses, and then another coroutine runs. So that is it. I have only 2. These are very important. I don't know, is my screen being seen? Can it show that it's sharing?
Yes, you can see your screen.
All right, I don't know if, but I wanted to show an example of how asynchronous code can be written. This is manual, so I don't know how to zoom it out. But it doesn't look nice. But in Python, if you're trying to build asynchronous code, we use a tool called Async.io. I don't know if people in the audience have heard about it, but we use Async.io, and it is the one that provides us with the tools that we need to actually build the asynchronous code. It mainly gives us the ability to build tasks, and also it gives us an event loop that is going to be able to run those tasks concurrently. So if you're viewing the screen, one of the things that we have to do is that we import Async.io up here, as you see, import Async.io. And then, like I said, we use the keywords called async and await. So on every function, so if you know how to write a Python function the normal way, the only thing you have to do is just add async, the async keyword in front here. Is it in now? Oh God, I don't think. Trying to zoom it manually. So anyway, we do async and then def. We're defining the Python function now, and we're giving it the function name and then the function parameters. You can ignore these int and float and then this. It's just part of the function prototype, the function signature. But they're only just used for typing purposes. Then we write the function, the asynchronous body. For this function, we want to print every number in the range of what is passed into the function. So what the coroutine does is that for every number n in range number that we're going to be passing here, print that number and then await. This await keyword is going to enable the event loop to pause this coroutine and then let another coroutine run, and then we shall come back to this coroutine later on. So here we have our main function that is going to run this asynchronous code. So our main function is defined also as a coroutine, which is async def main, and then this is just part of the function signature. Then we create tasks. the tasks is going to be a list of tasks that you are going to create that are going to be run by the event loop. And now here we are creating 5 tasks, which are all going to run this coroutine code one at a time, and until they get done, until they're executed. So like I said, the async IO library, it gives us an event loop that is going to be able to run this code for us. And in order to use it, we're going to use one function in the library, which is called gather. So I put the tasks into the gather coroutine, which runs all the tasks that I've given it to it at the same time until they get done. So here is now how I'm going to execute the code. Coroutines naturally are not run like how Python functions are run natively. They have to be run like how generators are run. They are called along lines of execution. So they're not, you can't call them inside the Python VM itself, the Python interpreter itself. You have to call it using an event loop. So here, that's why we're using async io.run. Async io.run is going to run our main event loop, which is going to execute asynchronously until the execution gets done. So here, as I was calling the function, the coroutine, I passed in the argument 5. So that means the coroutine that is going to run and print one value n in a range of 0 to 5 for every coroutine. So here is how it is going to go. And I've created 5 coroutines from here. I know it is not understandable at this time, but you shall ask questions. So here is how it's going to run. So if I run, you can see from the results, at first it prints 0, 0, 0, 0, 0. Then prints 1, 1, 1, 1, 1, 5 times. Then prints 2, 2, 2, 2, 2. Then 3, 3, 3, 4, 4, 4, and ends there. So the thing is, why it is doing like this, it's because one function is running, like printn is running once, because I've created 5 coroutines. Now the 5 coroutines are being run asynchronously. One runs at first and then it sleeps. That means it gives room for the other one to run. So if one runs and prints out 0, it gives room for the other one to run, which also prints out 0. It gives room also for the other one to run, which also prints out 0. Gives room for the other one to run, which also prints until the 5th one is done. Then it goes back to the first coroutine, which now also prints 1 and then it sleeps. Then it gives room for the other one to print out 1, which also sleeps. And it also gives room to the other one to print out 1 until like that. So it is like a cycle of coroutines which are running in a circle, in a loop. They run one at a time until they're done. So it is easy to break down tasks and then run them in an event loop. So you can be able to handle, here I've written only 5, but you can be able to handle millions of coroutines in this event loop, which just do one execution and block, and then another, give room for the other execution to run as well, which is very different from one of the mistakes that you're going to see here. I don't know. Is my screen still being seen?
Yes, Tobias.
All right. So this is still the same example as before, but I've removed one. I've commented out this line, the await async IO sleep. So you're going to see the difference in the results. Here in the results you see 0, 1, 2, 3, 4, then 0, 1, 2, 3, 4, then 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. In this case, it means that the coroutines were not running asynchronously. It means one coroutine first ran and it finished everything. Then after that, another coroutine came and then ran and finished everything. Another one came and ran and finished everything, which is not what we want to do. Because what if one coroutine takes a longer time and it does not end? It means it shall be blocking the other coroutines from running, which is why we say that asynchronous code is non-blocking. like what I mentioned earlier, non-blocking. And here, if we do this in this case, it means that a coroutine is blocking the other coroutines from running, which is not what we want to do. So a coroutine is supposed to identify when it feels like it is taking too much time to run a specific line of code, it should stop and then tell the other coroutines to run in its place as it is waiting. So that is why we have the await. If a code is taking long, it has to wait. And then when it waits, it gives room for the other lines or the other coroutines to run. So when it gets what it needs, it will come back and re-execute without blocking. This is the non-blocking that I'm talking about. You can see the difference in the results of code. Here, you see that one coroutine ran completely, which is not what we want. But here we see that they ran concurrently, which means you see one coroutine ran, it stopped, another one ran, stopped, another one ran, stopped, another one ran, stopped. Then they came back again. They began executing 1, 2, 3, 4, 5. Then they came back again, began executing 2, 3, 4 in that order. So giving room for each other to execute, which is generally what we want. So that was my last slide. If it wasn't for the internet connection, I would have finished earlier than this. But now I think I am welcoming any questions that you have. Yes, I don't know if I've been making sense, but we shall see from the questions out there.
Okay. Thank you very much, Tobias. That was a really, really insightful section. Thank you. I'm sure our audience really gained a lot. And yes, the floor is now open for questions. So if you have any questions concerning what Tobias just went through just now, you could ask your questions, and Tobias is here to give us an answer, right? Give answers to all of our questions. So bring it on. You can unmute your mic to ask your question. And if you're not comfortable speaking, you can also ask in the chat box, and I'm going to read it out. So we have about 10 minutes for that. So let's get it started. So if there is no question, would I just assume everything is so
everything was very clear. It was very detailed.
Is that it? Okay, seems that's the case. Is there no question, no contribution? Okay, hi, Ejiro.
Okay, my question to Tobias will be, when I notice you use the await, and if the whole point of asynchronous is to create non-blocking and fast-moving, let's say, coroutines, must it go round? Since it was asleep for only 0 seconds, did it have to go round before coming back to the first coroutine? Let's say it was asleep for 1 second. After, or let's say 0.0001 second. After it has run the first coroutine, run the second one, the third one, by then the first one will be ready for the next step. Should it not have gone back? And what if maybe somebody among the coroutines, there's a long or blocking one? Would it still wait for that one to finish before skipping? I don't know if you get the question. Do you?
I think I've understood your question.
Okay.
But so it goes down to the implementation. In my code, I've written, oh, I stopped sharing. Okay, as I'm pulling back the thing. In my code, I wrote, can you see it now?
Yeah, I can see your code.
Okay, yeah. I wrote, I think I sleep 0. That means it's sleeping for 0 seconds, meaning it's not even
So
sleeping
it's
at all.
not sleeping.
Okay.
Yeah.
Yeah. Okay, so here's the thing. The person who implemented asynchronous async.io in Python is the father of Python, and there's another core developer called Yuri Silvano. Now, in their implementation, what they did was that async.io sleep 0 is highly specialized in that it only tells the event. Why I use this normally is because this is specialized because it will tell the event loop to sidestep some internals and then quickly execute the next coroutine. Here's the thing. Imagine we have a queue full of let's say like I think you guys line up for food while at school. I think you did that. I'm sure because we do it here. So when you're in line for food, you're over 100 people in the line. And then like now imagine those 100 people are coroutines. Now, when the last person on that line will have to wait for the first person to first get food or maybe first get something. But if like you are in a buffet or self-service, and then someone is waiting, like the first person is waiting for greens to arrive because he wants to get greens. And at that point, he's blocking the whole entire queue from continuing because he's still waiting for the greens to arrive. But now when you see here, this asynchronous sleep shows that if someone doesn't see the greens, let them get off the line and then someone next goes in. It is much faster than telling them to first wait for 2 seconds until, or to wait for 5 seconds. If the greens don't arrive, then first move out. So the asynchronous sleep 0 tells that if you don't see anything, move out and then let the other coroutine execute. The event loop is implemented in C, so it is much faster than running Python code. And then you ask the other thing, which is, I forgot what you asked next.
It's the same question, but I just remodeled it. But let me remodel the question again to make you understand what I'm talking about. The reality of using asynchronous calls is that the different coroutines would have different time implication or different complexities. So let me use an example. A grandmaster is playing chess with 5 of his students, and he wants to go through this chess game asynchronously. So what he does is he goes from player to player, making just one move. So he starts with the first player, he makes one move. And while that player is thinking, he goes to the next player, makes one move, and it goes like that. So in the course of the chess game, a time comes when maybe a relatively slow player has still not made a move and he has gone around to meet that same player and he has not made a move. The ideal expectation is that he will skip that player again since he has not made a move and continue. And what that means is you may have, if there are 3 players, 1, 1, 1, 2, 2, 2, 3, 2, 3, 3, 2, 4, 4, 2, let's say 5, 5, or 5, 4, 3, you know, I don't know if you get the concept, because the player's speed will be different and the idea is to not stop at any point. So I'm asking, if the reality of this thing was not just this simple print statement, if I had different HTTP requests or requests on endpoints that will give response at different times, that's the key thing. One, I'm calling the database that is local, I'm calling a DB that is distant, I'm calling a HTTP service that takes some time or that runs a function and it takes some time for it to, or some task, it takes some time to return the response. And I'm calling a string of these things that have series of functions behind them. Would the asynchronous function in this very way you've written it be smart enough to even skip a process twice or a coroutine twice if it has to, just to ensure it uses the least amount of time? Or it's only just going around in circle and waiting for each person to attend to one by one? That's the question, really.
All right. So this, I've understood it now. This is an event loop. So it is going to, a loop goes round and around and around. That's what it does. So even though the player has not made a move, it will still come and check on that player. Even though it identifies that it's a slow learner or it's a slow player and it was not going to make a move even in the next round, it will still come and check on him. However, there are techniques that you can use to sidestep this. And now this comes down to the overall architecture of your back end. We have different techniques. We have the mediator pattern. We have the broker pattern. So you can use, okay, it's one of the things I was researching about, that exact thing that you said. I'm trying to work around it under one of my IBM studies. But the thing is, you can find a way I don't know if this is confidential, but there's a technique I'm trying to develop, which kind of tries to weigh the, like how you said, how am I going to identify a slow coroutine, and then I will be able to move it out and then maybe position it somewhere else. It's a very interesting technique that I'm working on, but it is different from how an event loop runs. Now it is a different implementation. Asynchronous programming is a whole entire paradigm. It is not only limited to async IO as implemented by the Python core developers. You can still also contribute something new. Now, like you've discovered that problem, you can try to investigate how to solve it better. Because now I'm also working on a way of investigating it personally. And there's some code I'm writing, but it identifies the coroutine through timing. And then it moves it out from the event loop to another event loop. So you don't run only one event loop, now you're running multiple event loops. Are you getting it? So there are many techniques that you can use. This is just an introduction. So once you begin exploring the idea further, you can try to play around with these loops in any way. So you can say you can use the technique I'm using is called a moving. I got it from garbage collection. It's called a moving GC, where you identify, you rate some certain coroutines, like let's say that coroutines which will never stop. For them, they will always run, they're infinite. So I can get them out of the main loop and then put them in their own thing and then leave the main loop limited to some sort of, I can create multiple loops and all of them are designed for specific tasks. So if I say that this coroutine is behaving in a way I don't want to behave it, I migrate it from that place and I put it somewhere else. So it's a moving GC. But the main techniques can be, this is introduction, so
okay. I think it's beautiful. I think what you've said is beautiful. It's a good thing to consider. I once had a task. I think it was just an assessment basically, and it was to query about 100 servers and do some formatting in the results. So I was also format the results to represent something in a log and something in the standard output. That's why I asked the question, because then I considered asynchronous back then. I read concurrency, parallelism, and this as in the single threading or the single line flow. So the single line flow is a common one most people do in Python, request.get this endpoint. But you see a little async in JavaScript especially for Node programmers. You see them use async a little, await and all of that. Promise, fetch, others they are Node.js terms. So that's why I first encountered this issue, and I had to debate between doing a concurrent something or a parallel process or a single synchronous thread process. So yes, that's why I raised this question, because I realized that the endpoints are not going to respond at the same kind of time, and there could be one that maybe fails several times, and you need to retry. You need to account for endpoints, and when you make a request to them, it fails the first time. Maybe you run 3-4 times where it goes through. So these are the things I was trying to factor in my decision. Can I set async to wait for only 2 seconds before it goes to the next coroutine? Can I make it intelligently test them? Things like that. But
you can. You just have to implement that code yourself because it is not there in the Sync.io personal. Yeah. But what I could say is that you can spawn 4 threads, like using multi-threading. You can spawn 4 threads. Multi-threading will also Python doesn't do good with multi-threading. But let me say you can spawn 4 threads if you're using in a C code. Spawn 4 threads, and in those 4 threads you run 4 event loops. And each event loop is going to be responsible for running a certain kind of characteristic of coroutines. Let's say if the main event loop, if it wants to run fast ending coroutines, that will be the coroutines it will run. If it identifies that there's a coroutine that is taking much time, the timing functionalities in Async.io. So you can maybe time a coroutine, and you say if it is taking time, move it from the first thread into the next thread, which is going to wait on it. It's like patience, let's say.
Yes.
If you're in a hospital, if the person is taking time, like, okay, you can see doctor this as I'm handling the patient number 2. So maybe Dr. Samuel or Dr. will be able to handle that person at that slow rate. Then if Dr. Samuel doesn't understand this person, we'll take them to Dr. maybe Samson or Dr. Are you getting it? So you're just moving it through various event loops. It's just a technique that you can implement on your own. It doesn't have, maybe there's a library, I don't know, but you can implement it on your own because I'm also implementing it on my own.
Okay,
From research anyway. So.
That's nice. I think what one of the things you said is very cool. A smart combination of parallelism or multi-threading and asynchronous call.
Yes, that is it.
Your inbuilt configuration on like the patience tolerance or something within async. That's fine. That's a good one. So I think that's it from me. Thank you.
You're welcome.
Brilliant. Thank you very much, Tobias, and thank you very much, Ejiro. That was, I was just thinking like both of you going back and forth. I'm like, okay, what are they talking about? But I'm sure the rest of you audience totally understand the whole patience, threading, everything. Thank you very much, Tobias, for asking brilliant questions. And
yeah, you're welcome.
Thank you, Tobias.
Is there any other question? Or that
delivering answers. Yeah, that was what I'm about to ask. So is that other question? Is there no other question? Yusuf, Muli, Victor, Samuel, Julia, no other question? Or is it because you're not allowed to speak? Okay, someone is.
Sorry, I just wanted to add.
Okay, Yusuf, hi.
Hi. I wanted to ask, I've seen him explain about Async.io. I've never come into contact with any use for Async.io, but I've worked with a client who was using Fast API, which uses, yes. I always wondered what would drive someone to choose to use, say, Fast API. What kind of scenario is it best for?
Okay. So here is the thing I should describe. It is the same battle that we had between Apache and Nginx. If you try to read through a lot of research papers and a lot of articles out there that we compare, and the Nginx server has always won because of the technique it employs. So because of that, even back-end techniques have begun migrating from multi-threading because Apache uses multi-threading, which, like I said, a single thread incurs a lot of cost on a CPU. Now imagine 6 million threads will break data that you're having. That is why it takes a lot of server resources and it is not scalable. And the coroutines are lightweight and they don't even impose a lot of strain on the operating system. They just fire a single thread. So Nginx can be able to handle millions or billions of requests if you have Nginx clusters. They can, like let's say 6 Nginx servers can handle 6 billion requests, let's say. And you'll need hundreds of similar Apache servers to handle that kind of request. So because of the asynchronous technique, even Python itself began developing tools to utilize Async.io. And it moved away from what we call the web server gateway interface, which is WSGI, that is used by WebPy. They all use WSGI. Moving on now, which is called ASGI, Asynchronous Gateway Interface, or my network. Is my network okay? Am I breaking up? Hello?
You are breaking, but we can hear you.
I hear you now.
Oh yeah. Okay, but okay, now let's say in the Python world, it is a battle between two protocols. It is a battle between WSGI and AS. You can find that out. The ASGI is a modern one, which helps you utilize the power of a sync IO to build a synchronous servers, which they're not fast. Let's just say they're not fast because they'll still be using the CPU, the same CPU that other servers are going to use. The only difference is that they will help you utilize your CPU to full potential, which is not what threads do. Because of the blocking nature of threads, they lie there idle, doing nothing and wasting memory. So if you just only have 4 threads, which can be able to handle 6 million people, instead of having 6 million threads which lie there being idle, doing nothing, you'd rather take the other option of having 4 threads that will be able to handle the 6 million people, because it doesn't waste resources, it utilizes all resources, and it is minimalistic. It can be easily maintained. And Fast API is modern. It is lovable. It is fast because it competes with languages like Go, which are super fast as well, because Go is compiled. But if Fast API is able to write backends, which can be able to compete with the likes of Go, yet Django in itself cannot. If you look at the Tech Empower benchmarks, yeah, I think it's called Tech Empower. If you look at the Tech Empower benchmarks, you can see that there's Starlet is the fastest backend Python framework, and it uses async IO. Then the next one is Fast API, which is also built on top of Starlet. So it's just riding on Starlet's power. Then you'll find the other Django's, which are very far ahead because they're very slow. So the thing is that, first of all, it is fast because it helps you utilize the CPU efficiently. And it also helps you use limited resources. So that means your backend can be able to scale very efficiently. You can use one server to handle many requests. It can be do with the protocol, because there you need many physical servers. So you need to scale vertically and also horizontally. But for the Fast API, you can only just even have it. It will take time to scale because your backend is adaptive. And I don't know if I've made sense at all. I've been saying things randomly. But have I answered Mr. Yusuf?
Yes, you have somewhat.
Yeah.
But I'm wondering about the criteria that you would say, I think I should use async for this particular problem instead of the normal of doing it with Python.
Okay, I think IO.
Yes, especially with when it comes to web.
Hi.
So the keyword. Oh, someone saying something. Okay, but I was saying that
I thought I heard someone say something.
Yeah, I heard also someone. But when it gets to async IO, the keyword is IO, because IO is very slow. You don't have to apply async IO to anything that is CPU intensive. So that means if you're making very fast calculations like graphics or things that require a lot of CPU crunching, don't use async IO. Async IO is used on blocking like networking code, which is slow. That let's say if you're reading a file, yeah, you can use async IO to read various files. If you're reading off a network, you can use async IO to read off networks. And that is if you have various coroutines which are trying to read off various networks at the same time. So that is where it can work. But if you're playing a game and you're trying to use async IO somewhere, it won't work for you. It will just be wasting your time. It won't help you in any way. So async IO just helps you remove the weighting of your code because you realize that if you, let's say like how we're struggling right now, we're having lag between me speaking and then you hearing the actual audio. So I think it's just in eliminating that wait time, where you have to wait for something to work. Instead of you waiting for me to speak, you could be running another task. And if my message comes to you, then the task that was waiting for me to speak could run whatever it wanted to run after the message has arrived. It is like, that is the way it is. It doesn't increase CPU power. It just helps you handle a lot of connection, internet connection, reading files, things like that. That is the key word, I should say. And where it is applied is basically in back end nowadays. Every modern Python back end, I suggest, should be written using techniques, because it is much faster. Okay, no, it is much easier. Okay, it is better. Yeah, but it's faster. It is better. Yeah.
Yeah. Thank you very much, Tobias. Thank you, and thank you, Yusuf. I think Julia has a question. Yes, Julia,
yes.
please.
Hi, Bami.
Go ahead. Hi, Julia.
So I wanted to answer the question that he had of, like, I think he asked to give him a real life example of asynchronous programming. Was that what he asked?
Is that for Yusuf?
Yes.
Okay. Yusuf, is that what you asked? He said an alternative. He's asking for an alternative.
Yes, a real life example would help, but I think Tobias explained how you determine that I think I should move to async IO in this case instead of the normal procedure.
Okay, because I wanted to explain it like in the example of a chat system. Let's say the way we use our WhatsApp. It's a real example of asynchronous programming, whereby you do not need to keep refreshing your WhatsApp. So there's asynchronous programming channels that go on, whereby whenever someone sends you a text, you will receive it immediately you're online. So that's a good example of asynchronous programming.
Oh.
Cool. Thank you very much for that, Julia. Also, I think, Julia, you have a question, right? Can you ask your question now?
I was asking the question that they asked. They were trying to deliberate in the beginning. Can't you just use a celery task to hand over whatever needs waiting?
Is that for Tobias?
Yes.
I've not understood what you've asked.
So let's say you were saying that there are tasks, whatever the discussion that you had, you had a question, or you were trying to come up with a solution on how to have that patience.
Oh.
Yeah, can't you hand over those tasks to, let's say, celery?
Celery, yeah, you can actually, because it's a process manager.
Yeah.
But I don't understand. I don't know if celery has ability to understand coroutines as yet. I think it's more suited for multi-processing, because it spawns processes all the time. But in this case, celery hasn't yet had the ability to understand async IO. Let's say it hasn't yet, not understand, but they haven't added those features of how to fully like implement or take or use celery. You could use it, you could find your own way of playing around with it. Like you could find ways of doing it, but celery as in itself, it hasn't yet. You could even say the same thing with GUnicon or Uganicon, how people call it. It's a process manager, but doesn't really understand async IO as yet. It spawns processes and manages them, it is not what we want at this point, because processes are even worse than threads. Processes have their own issues, which they are fast, they are good, but they only need to be used when you're doing something that is CPU intensive. So right now, Celery doesn't understand Async.io very well, but I'm sure maybe they're working on some way of bringing it. But you could do what Celery does. You determine what coroutines are taking a long time, and maybe spawn a process for them and put them there so that they play around there. It's like how they do it in class. If you find that they're very smart kids, you get a class of their own, and there'll be a class of smart kids. And you get the medium ones and put them in the class of the medium people. Yeah. And the real one, the people who need help, you put them in our class. So you have like a one class having different streams. So you could use a technique like that. And I think that some research has been done in it. I think you can even find research papers out there. But in native code, like in Python itself, you'll have to do some of those things yourself. That is the thing. If you identify a problem, you have to, because Async.io is just a framework. It just gives you a skeleton. It's up to you to build the flesh off of it and use it however you want.
Okay.
All right.
Interesting. That was a very good one. Pretty insightful. Thank you very much, Baz. Thank you. And thank you, Julia. Oh, we have one more question. Can we still take more? Tobias?
Let me call it a contribution.
Okay.
So while he was speaking and he mentioned speed, I also looked up the 10 power ranking or benchmark. And I found out that a form of Async.io HTTP request library exists, or framework, AIO HTTP. And within it, you can set timeout and all. For the context of the question I asked, timeout is what will do the job. So maybe you are trying to call an endpoint and it's taking too long, you can time out.
You can time it out.
You can come and retry. So AIO HTTP is even faster than the Starlight mentioned. It's about fourth ranking. It's quite high.
AIO HTTP is good. It was implemented by someone I know. It's called Andrew Svetlev. I don't know those Jewish names, whatever they are. But it has issues. It is also slow compared to Starlight. But yeah, it has good work. But if it comes to back ends, it's somehow slow. If you're using it for client side code, it is extremely fast compared to Starlight. So yeah, but you can use timeouts. Timeouts, if something is taking too long, you can time it out. But the thing is that a timeout will cancel the execution. That means you won't have a time to resume it again. So that is why I was suggesting that instead of timing it out completely, you could just move it somewhere else where it can still run. Because if you time it out, it will cancel the and fresh. That is the thing that I wanted to avoid at that time. So you can just move it somewhere. That's why I'm suggesting a moving GC. You just move it somewhere where it can still run. It takes its time, but it creates room for the other coroutines to run as well. You don't absolutely kill it off. So that is the thing with the cancellation. Timeouts just do cancellations.
Okay, I'll read it up.
Great.
But yeah, just wait for me to publish my paper first before you use that technique.
Nice.
Okay. All right. Nice. Thank you very much, everyone. Thanks for joining today's episode of Tunga on Expert Tuesday. And I really love the whole conversation with the whole interaction with